Hello, my name is Mohammad Arabi. Thank you for choosing to watch my presentation today. I am a graduate student at the University of California, Irvine, and a member of the Autonomous Systems Perception, Intelligence, and Navigation Lab, or ASPEN for short. Now, my presentation today is going to discuss opportunistic navigation with Doppler measurements from multiple low Earth satellite constellations, specifically the Iridium Next and Orbcomm constellations. Now, ever since the development of global navigation satellite systems, they have been the leading providers of position navigation and timing services, or PNT for short. But these systems have some well-known vulnerabilities, and the need to address them is becoming more and more critical as we move towards a more modern world, where instead of pulling up your phone to order an Uber, you can order a UAM or urban air mobility vehicle, and where packages you order online could be delivered to you within minutes via UAVs. Although these things might seem futuristic, Uber already has plans to launch Uber Air in 2023, and some of you might have even heard of Amazon's Prime Air as well. Now, generally speaking, these autonomous vehicles depend on GNSS along with some other sensors such as IMU, LiDAR, and so on and so forth. But is that enough to prevent any accidents? And what kind of performance would we expect if the GNSS signals were compromised? Well, we were invited by the Air Force to conduct an experiment in a GPS-denied environment, where we drove a car into an area where GPS signals were being jammed. As you can see, the red curve, which represents the GPS IMU solution, drifts significantly, and this is using a $10,000 GPS IMU system. If we just use our phones instead, this is what Google Maps was showing. You can see here that the blue uncertainty halo was much larger than usual, and at some point grew up to 6 kilometers. So how could we deal with this? Well, one solution is turning to signals of opportunity, which are signals that weren't designed for navigation purposes, but can still be exploited to produce navigation solutions. Now, if we take a look at the blue curve, we can see that it does much better in GPS-denied environments. This curve represents the navigation solution produced using only one SOP from a cellular tower. In this presentation, however, we will be focusing on SOPs from low Earth orbit satellites, or LEO satellites for short. So what kind of opportunities do LEO satellites provide over GNSS satellites? Going down from an altitude of 20,000 kilometers to an altitude of just 1,000 kilometers results in a significantly more powerful signal at the receiver. LEO satellites are also abundant. As of September 30, 2019, we already had about 1.5 thousand satellites in low Earth orbit, and that number is expected to rise significantly to around 107,000 satellites by 2029. These satellites can also provide better geometric diversity, which in turn translates to a more accurate navigation solution. LEO satellites also provide more spectral diversity, as their signals span a significant portion of the radio frequency spectrum, making LEO-based navigation solutions more robust against malicious jamming and spoofing attacks. And, in addition to all that, these signals are also free to use, which is always nice, especially in the way we exploit these signals at Aspen, where navigation solutions are produced opportunistically and without having to subscribe to the company maintaining the satellites. Now, all these opportunities provided by LEO satellites have triggered a renaissance of research in LEO-based PNT solutions. And the approaches in the literature could be grouped into three main categories. So in the first category, LEO satellites are assumed to be equipped with navigation payloads similar to GNSS satellites. These approaches can achieve GNSS-like performance, but they might not be the best option, as the additional cost of the payload would have to be incurred by the company or its users. In the second category, LEO satellite signals are fused with GNSS signals, with the goal of reducing the dilution of precision and increasing robustness against spoofing and jamming attacks. And last but not least, we have the third category, with fully opportunistic approaches, which is similar to the previous category, except that the GNSS signals are dropped, so they only depend on signals from LEO satellites to produce PNT solutions. However, as with everything in life, there is no free lunch. LEO satellite-based navigation also presents several challenges. For starters, we don't always know how the signals look like. Signals from these satellites are not fully documented. We don't have any interface control documents like we do with GPS, for example. And sometimes even basic information such as modulation and multiple access schemes might be proprietary. Also, since these satellites are not designed with the purpose of navigation in mind, they don't necessarily transmit any ephemeris data. And even in the occasions that they do, we might not have access to that data as non-subscribers. A common way around that issue is using two-line element or TLE files to estimate the satellite positions, but these estimates might be off from the true position by up to 5 kilometers. The clocks on LEO satellites are also not as stable or as tightly synchronized as GNSS satellites, which makes it more challenging to get an accurate navigation solution. And on top of all that, we also need to build specialized receivers that are meant to extract navigation observables instead of the existing receivers for those constellations that target data. If you're interested in this topic, you can also watch other members of the Aspen Lab present their work at this very conference, tackling the challenge of unknown signals and mitigating the large satellite position errors. Now, for the main contributions of the paper, we tackle the problem of designing a specialized receiver architecture that is capable of extracting Doppler measurements from MPSK signals transmitted by LEO satellites, whether they are being continuously transmitted or are transmitted in bursts. We also demonstrate the proposed receiver for the Iridium Next and Orbcomm constellations, and to the best of our knowledge, produce the most accurate experimental results for multi-constellation LEO satellite-based navigation, offering an accuracy improvement of 83% over what was previously achieved in the literature. So to understand the significance of using multiple constellations as opposed to just one, we need to take a look at the limitations of utilizing only one constellation. Nowadays, sophisticated GNSS receivers don't just use signals from GPS or GLONASS or Beidou, etc. They use the signals from all of these constellations simultaneously. And if we don't do the same for LEO satellites, then we are, first of all, limiting the number of satellites that we can listen to, and limiting the geometric diversity that they provide, and even limiting their spectral diversity, as satellites from the same constellation typically transmit in the same frequency band. So in short, to truly harness the opportunities provided by LEO satellites, such as abundance and geometric and spectral diversity, we need to be able to exploit signals from multiple constellations simultaneously. To further illustrate this, we use the Orbcomm and Iridium constellations as an example in this figure, which shows the percentage of time X or more satellites are simultaneously visible over a period of 5 days, which is approximately the period that it would take for these satellites to have the same configuration. The satellite trajectories were simulated using TLE files and SGP4 propagation software. This figure shows how the probability of listening to X or more satellites decreases rapidly when we limit ourselves to only Orbcomm or only Iridium satellites, but decreases a lot slower when we increase our options to both of these constellations. Now, to be able to do that, we need to develop a general signal model. So first, if we denote by U the number of constellations available, and by L sub U the total number of satellites for each constellation, we can model the received signal for the Uth constellation as the sum of the signals from the individual satellites in that constellation, plus a complex noise term with a variance of N0 over 2TS, which is assumed to be independent and identically distributed across channels. Next, we model the received signal for the L satellite in the Uth constellation as follows, where the term A sub L sub U denotes a symbol drawn from an MPSK constellation. So to help visualize this model, we can look at the following figure, which shows how every satellite in any constellation is transmitting at a different frequency and or at different points in time. So this signal model holds for both continuous and burst signals, and the difference between those two lies in the domain of the time index I. For continuous signals, I goes from 0 to infinity, but for burst signals, I is only defined over the burst intervals. And to be able to define it this way, we need to have knowledge of the burst duration and period, as well as the burst start time, which could be acquired at initialization with a simple energy detector. So to set up our proposed framework, you only need prior information about the burst period and duration, as well as the number of points in the MPSK constellation. And now I am going to walk you through our proposed framework, which performs 6 steps iteratively. So first, we have intermediate frequency wipe-off, where the received signal is multiplied by a complex exponential with a frequency of negative FIF. Next, the resulting samples, denoted by D sub L sub U, are grouped into data blocks of duration T burst, which is specific to each constellation. In the grouping process, a number of samples are dumped each time, with a duration equivalent to T dump, which is simply the duration of the burst subtracted from the period of the burst. Naturally, setting the burst period equal to its duration would result in no samples being dropped for continuously transmitted signals. Next, these data blocks are raised to the mth power to wipe off the MPSK symbols, resulting in a pure tone at m times the Doppler frequency. Next, the fast Fourier transform of the latter signal is taken, and of course, since it is ideally a pure tone, it results in an impulse-like peak at the tone's frequency. Now, the receiver tracks the Doppler over time by looking at the FFT peak in a window centered around the previous Doppler estimate with a size of 2 delta f. Now, the last step should only be performed for burst signals. In order to successfully track a burst signal, it is important to update the burst start time acquired at the initialization of the receiver. This is due to the change in the distance and hence delay between the satellite and the receiver. Luckily, we already have something that relates to that term, and it happens to be the navigation observable that was just extracted. The Doppler frequency is given by the following equation, and we can calculate an upper bound for this term by using the lowest possible altitude of LEO satellites, which dictates how fast it has to be moving. So this term is small enough to approximate the Doppler frequency with the following equation. And if we then solve for the line of sight velocity and then multiply by the burst period and divide with the speed of light, we can compute the change in the burst start time. This change is accounted for by dropping a few more or a few less samples, causing slight variations in the value of T dump and making it satellite specific instead of constellation specific. Now that we have extracted Doppler measurements, we need to feed them to a filter to produce a navigation solution. The pseudorange rate measurement model could be formed according to the following equation, and for compactness of notation in this section, the subscript U denoting the constellation is dropped. Now, it is safe to assume that the receiver and satellite's clock drifts are constant for the 10-minute window of LEO satellite visibility. And since it is not necessary to estimate the receiver and satellite's clock drifts individually, they could be lumped into one term. We also assume that the ionospheric and tropospheric delay rates are either insignificant or approximately constant within that brief duration, and could be lumped into that term as well, which yields the following approximation for this model. Now that we have developed a measurement model, let's take a look at the extended Kalman filter. The state vectors to be estimated are the receiver's 3D position and the previously mentioned term lumping the receiver and satellite's clock drifts for each satellite. Therefore, the measurement Jacobian was derived to be as follows, and for more details, I invite you to look at the paper. It is also worth noting that the receiver was assumed to be stationary, which theoretically means that the process noise should be set to 0, but in order to prevent the estimation error covariance from converging to 0, it was set to a very small positive number instead. Now that we have introduced the navigation framework and filter, we are going to give you a very quick overview of the Iridium Next and Orbcomm constellations. So first, for the Iridium Next constellation, it has 75 active satellites in 6 different orbital planes at an altitude of 780 kilometers. These satellites transmit signals over part of the L-band, and as for the signal of interest, it is the ring alert burst signal, which has a bandwidth of 35 kHz centered at 1626.27 MHz. We also know that this burst signal has a duration of 2.56 milliseconds and a periodicity of 4.32 seconds. Now for the Orbcomm constellation, it contains 42 active satellites in 7 different orbital planes with an altitude between 740 and 975 kilometers. Signals from these satellites are transmitted within the very high frequency band, and the signal of interest here is a continuously transmitted QPSK signal with a bandwidth of 1 MHz centered at 137.5 MHz. Now, to test the proposed navigation framework, An experiment was conducted at the roof of a parking structure at the University of California, Irvine. We used two Universal Software Radio Peripherals, or USRPs, to collect multi-constellation LEO satellite signals. One USRP was equipped with a very high-frequency helix antenna to sample Orbcomm signals, and the other was equipped with an Iridium antenna to sample Iridium NEXT signals. Both USRPs were set to sample data at a sampling frequency of 2.4 megasamples per second over a 410-second duration, which is about 7 minutes. The samples were then stored for offline processing, and a software-defined MATLAB implementation of the proposed receiver architecture was used to post-process the collected data. As for the framework, we had 3 parameters to set up for each constellation. So in this experiment, the framework was set up as follows. As a reminder, the signal of interest for the Iridium constellation was a pure tone that was transmitted for 2.5 milliseconds every 4.32 seconds. And for the Orbcomm constellation, the signal of interest was a continuously transmitted symmetric differential QPSK signal. So theoretically, we should raise the signal to the 4th power. However, for this type of modulation, raising it to the 2nd power resulted in a more powerful peak to track, and here's why. So this is how the phase of a symmetric differential QPSK signal evolves over time. And on the right, you can see how the signal would look like in the frequency domain. Now, if we raise the signal to the 2nd power, its phase would always look like this, oscillating between plus and minus 90 degrees. Now, to help you see why this is the case, first we have to notice that due to the modulation, the phase of the signal always changes from one symbol to another, and that this change has to be to a neighboring phase. Now let's take a look at what is happening to these phases. The 2 phase levels in green would be mapped to the same phase of plus 90 degrees. And the 2 phase levels in red would be mapped to minus 90 degrees. And so for any binary sequence that uses SDQPSK, this is what we would see if we raise it to the 2nd power. And again, on the right, you can see the signal in the frequency domain, and it has multiple peaks. And of course, if we raise the signal to the 4th power, there will only be one phase, resulting in a pure tone and one peak. However, these frequency domain representations are for a very high signal-to-noise ratio, and if we were to choose a more realistic SNR, we would see something more like this. So for m equal 4, the noise floor becomes higher than the peak amplitude, and we would not be able to track the Doppler frequency. But for m equal 2, we can still see the 2 main peaks, and we know that they are spaced 4.8 kilohertz apart, which is the symbol rate, and centered around the Doppler frequency. So again, this is why we set the number of symbols in the constellation to 2 instead of 4 when setting up our framework. The receiver produced Doppler measurements for 5 satellites, consisting of 1 continuously transmitting Orbcomm satellite and 4 burst transmitting Iridium NEXT satellites. These measurements were provided at a rate of 100 milliseconds for the Orbcomm constellation and a slower rate of 4.32 seconds for the Iridium NEXT satellites. The figure on the left shows the true and estimated pseudorange rates obtained from the TLE files and the receiver respectively. The figure on the right shows the time history of the number of available satellites. It is clear that there was 1 Orbcomm satellite in view for the entire duration of the recording, and 4 Iridium NEXT satellites come in and out of view at different times of the recording. We should also note that the satellites were not all tracked for the entire duration of their availability. And now let's move to the results of this experiment. The following video shows the time history of the EKF position updates on the right, along with the corresponding east and north errors at the bottom and the satellite's TLE position estimates on the left. The horizontal position estimate was initialized around 200 kilometers away from the receiver's true position, while the receiver's altitude is assumed to be known. And now finally, in the figures on the left, you can see the receiver's true position along with the initial estimate and the initial 2 sigma uncertainty. And below that, you can see the final 1 sigma uncertainty and the final estimate, which turns out to be 22.7 meters away from the true position. And on the right side, you can see the trajectories of the LEO satellites during the experiment, as well as the sky plot showing the satellite's elevation and azimuth angles. Finally, I would like to thank the Office of Naval Research and Department of Transportation for supporting this work, and I would also like to thank you for watching my presentation. And if you have any questions, I would be happy to answer them.